Hello, this is Dr. Strickland. In this video, we'll be talking about organometallic reagents involving lithium or magnesium. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. Okay, so first of all, I have a question for you. Think about the substitution and elimination reactions that you know so far, SN2, SN1, E2, and E1. Using one of these reaction types, do you have a way to make this compound from the given starting material? So this is bromobenzene, and my target is ethylbenzene. Now, if I had to first classify it as a substitution or elimination reaction, I'd classify it as a substitution because something has replaced or been substituted for a leaving group. If I had an elimination, I'd have a new double bond formed. Now, if you take a look at the hybridization of this carbon, it's sp2. And with SN2 and SN1 reactions, the carbon has to have an sp3 hybridization. So there's no way to make this target using the reactions that we know so far. However, if we branch out just a little bit and start to talk about organometallic reagents, we'll find a way to do that. Now, in these reactions that we've talked about so far, carbon has been an electrophilic atom. So when it's attached to something that's more electronegative, a leaving group like a halogen ion or something with an oxygen in it, then you know that you can have a nucleophile come in and do this because the carbon is electrophilic. It's got a partial positive charge on it, and that gives you a substitution product. Like that. Now, when carbon is bonded to something that's much less electronegative than itself, like a metal, then carbon becomes a nucleophilic atom. And in this case, we've got something that looks like this. Okay, so in this case, carbon has a partial positive. In this case, carbon has a partial negative, and we would end up with something that looked like this. Okay. So an organometallic compound is an organic compound containing a carbon-metal covalent bond. The greater the polarity of the carbon-metal bond, the more reactive the organometallic compound will be as a nucleophile and as a base. All right, so in order to find out what the electronegativity difference is between carbon and the metal, you just have to find the values on the table. For example, carbon is right here, that's 2.5, and then lithium is right there. It's 1.0. And so we've got these absolute value signs on it. So it doesn't matter which one you put in there first. We just want to know the difference. So what I want you to do is pause the video and find the electronegativity difference for carbon and magnesium, carbon and copper, carbon and palladium, and then come right back. Okay, welcome back. So with carbon and magnesium, we're talking about 2.5 minus 1.2. The electronegativity of magnesium is a little higher than lithium. That makes the electronegativity difference a little smaller. And this bond is less polar and less reactive because of that. If we come on down, carbon and copper, 2.5 for carbon, 1.8 for copper. Okay, so a metal that's more electronegative. Now the electronegativity difference is 0.7. A lower electronegativity difference means a less polar bond, means a less reactive bond. And finally, for palladium, palladium has an electronegativity not so very different from carbon. It's a little bit less, but just a tiny bit. So this is the least reactive carbon metal bond that there is. So a larger electronegativity difference gives you a more polar covalent bond. And a larger partial negative charge on the carbon bonded to the metal. That's going to make it a stronger base. And it's going to make it a better nucleophile. All right, so let's see how that makes a difference in the things that we're going to talk about. So these organometallic reagents involving lithium or magnesium are the most reactive ones that there are. And if you want to synthesize one of them, what you need is an appropriate alkyl halide and then the neutral metal. So lithium metal here, magnesium metal here. And halogens can be chlorine, bromine, or iodine. And these can be alkyl halides, vinyl halides, or aryl halides. Remember, with vinyl halides, the halogen is going to be bonded to an sp2 carbon of a carbon-carbon double bond. And in an aryl halide, the halogen is bonded to an sp2 carbon of a benzene ring. Alkyl halides are just the ones we've been using that we classify as primary, secondary, or tertiary. And occasionally they're also allylic or benzylic. So to make an organolithium reagent, we need whatever alkyl halide we're using plus 2 equivalents of lithium metal in a solvent that doesn't react with much, in this case, hexane. And so an organolithium compound looks like this. And the other product, not an organic product, but the other product is the lithium halide salt. So what I want you to do is I want you to predict these two products. Take 30 seconds, pause the video, and draw me the structure of those products. All right, welcome back. So the R group from the alkyl halide with the carbon that used to be bonded to the halogen, now bonded to the lithium. And then there's the other product. And here, this is an aryl halide. There will be a covalent bond from that carbon of the benzene ring to the lithium. And then again, salt. Okay, now if you come over here to organomagnesium reagents, these also are called Grignard reagents. And so you're going to mix the alkyl halide with the magnesium metal. The solvent is different. It's an ether solvent of some sort. Diethyl ether you've seen before. Tetrahydrofuran, I want you to look up. It's a cyclic ether. But again, like with the hexane, they don't react with much. And so that makes them really good solvents. But in this case, the metal is going to insert itself between the alkyl group and the halogen. So using this general reaction pattern, I want you to predict these two products. Okay, pause the video, do that, come right back. All right, welcome back. So only one product for us. The magnesium inserts itself between the carbon and the halogen. And I've been using bromine. It could be chlorine, it could be iodine. And then down here with this vinyl or vinylic halide, same kind of thing. All of this part of the molecule stays just the way it is. And then we're going to insert the metal between the carbon and the halogen. Good. Now, because these two kinds of organometallic reagents are so reactive, there are limitations on other functional groups that can be in your alkyl halide. The ones that we use very often don't have another functional group in them, but if you're in a lab and trying to make a larger, more complex molecule like an antibiotic or an anti-cancer agent, then very often there are going to be lots of functional groups in there. And so if you want to make an organolithium or Grignard reagent out of your alkyl halide, you have to know that it's because it's such a really good base. The alkyl halides that include a functional group like an alcohol, a thiol, an amine, an alkyne, or a carboxylic acid can't be used because this acid-base reaction, the deprotonation of the acidic group, will be faster than the organometallic forming reaction that you want. Now, the other caveat to this is illustrated here, and is something that will come up in lab. So, no water anywhere. Not in your glassware, not in your solvent, not in your reagents. Because if you do, what's going to happen is this. Okay, so remember there's a hydrogen there. So you would initially form a few molecules of this, but then these electrons right here attack the water that actually conceptually like this. And boom, you have destroyed your Grignard reagent. Now, sometimes when you're reading in your textbook, you'll see that there are times when people do this with deuterated water, D2O, in order to put a deuterium into a molecule. So people do it on purpose for those reasons. Okay, so stop here and answer the question at the end of the video, and then come on back.